Welcome to Chapter 5, Part 3. We're going to talk about naming and chiral centers, but I want to take a moment first just to talk about the importance of this thing we are discussing called chirality. When we look at our example of a few different compounds here, these are carbones. So we're going to learn that these chiral centers, right? The only thing that's different about the left and right hand structure here is they're non-superimposable mirror images because of this chiral center I have highlighted in red. The orientation of the groups on that chiral center make these a pair of enantiomers. All right, one is R, one is S. We'll discuss how to make that determination in a minute. If these are enantiomers, something to note is they're going to have identical properties in almost every way. They're going to have the same boiling point, the same melting point, the same densities, the same, oftentimes the same way they look. But they will have a couple of key differences. Optical activity, which we'll talk about in Part 4, but also just the way it behaves with other chiral compounds, like biomolecules. For instance, one of your carbones will smell, and I'm not going to say which is which because I don't have that in front of me, but they smell different. Your olfactory receptors can tell the difference. One smells like spearmint, and the other one smells a little bit more like pickles or like caraway seeds. I have a hard time telling the difference, and when I was in college, my professor passed around 2 sample vials, one of R, one of S, and asked about 70 of us if anybody thought they smelled the same, and only me and one other person raised our hands. And he said, we have floppy receptors, but most people can tell the difference. That's kind of a benign difference, right? It does interact with receptors in your body differently, but those different enantiomers can have bigger effects. So when we look at something like our analgesics, like ibuprofen and naproxen, they exist as enantiomers. With ibuprofen, oftentimes you will get a mixture of the two because one has analgesic properties and the other one doesn't really do anything. But naproxen must be purified because, just work with me there, must be purified because one of the enantiomers is an analgesic and provides pain relief, and the other one is toxic to your kidneys. And so it's really important that we understand this stereochemistry difference because it can have a pretty big effect on its biological activity. So hopefully I've sold you. You're now very excited about learning about RNS and how to make that distinction. And so to do that, kind of like when we looked at the cis and trans isomers, if these compounds here are different, then they need to have 2 unique names. And so like cis and trans for the rings and the double bonds, Coningal Pralog will help us deal with enantiomers, with chiral centers, and designating each chiral center with an R or an S. Now, there are 4 rules to follow. And we'll come back to the chlorobutanes. You need to prioritize your 4 groups. So you're going to have a carbon with 4 groups attached, 1 to the front, 1 to the back, 2 in the plane. You're going to prioritize using atomic numbers. And you are going to arrange it so that the 4th priority is always in the back. That's how these rules work. And then you're going to assign priority. So let's do something easy here. Let's use our halogens. I'll put fluorine. No, that's a 5. Hold on. Fluorine in the back, and then I'll just arrange the rest of them. Chlorine, bromine, iodine. I'm going to draw the mirror image. Chlorine, bromine's looking at each other. Fluorine still to the back. Iodine to the front. Okay. Iodine is the largest atomic number, followed by bromine, chlorine, fluorine. Can do the same thing on the other side. 1, 2, 3, and 4. Then you are going to count the priorities 1, 2, and 3. You're going to connect them. And so, because the 4 is in the back. So 1, 2, and 3 versus the enantiomer 1, 2, and 3. Notice one goes counterclockwise, one goes clockwise. S goes with counterclockwise. R would go with clockwise. So it allows us to give an indication of the exact determination, and that's your fourth rule over there. All right, so you are going to prioritize based on atomic number. You're going to arrange it so that the fourth priority is in the back, or you're at least going to learn a rule about that. And then you are going to connect 1, 2, and 3. Clockwise is R, counterclockwise is S. Now, you're not always going to have as straightforward an example as this one we just drew, because you're oftentimes going to have pieces that are all organic. And so you'll see that you'll have to have a tiebreaker when you run across carbon v carbon. So let's look at that example from the previous slide. Let's look at 2-chlorobutane. Now you can draw the enantiomer by just flipping the wedge in the dash. You can draw the enantiomer by just reflecting it through a mirror. Either way is fine, and you'll get the same answer. But let's address the rules here. So let's assign priority. Well, chlorine, we'll put in the little hydrogen back here. Chlorine is going to be number 1, and hydrogen is always number 4 if you have a hydrogen. And that's true on both. But then you have carbon versus carbon. And so you have to use the other things it's attached to. You're never going to go back towards the chiral center. You're going to look at what else is it attached to. This is attached to 3 hydrogens, and you're going to write them down in sort of decreasing order. Here they're all hydrogen. On the one on the right, you have a carbon, right? Looking at this guy out here. And then 2 hydrogens. And the first place it is different is your tiebreaker. Carbon has a greater atomic number than hydrogen. So this side is 2. This side is 3. 1, 2, 3. This first one that is drawn is clockwise. So this is going to be R. 2-chlorobutane. Now, when we reflected it through a mirror, it's just as easy because the hydrogen winds up still being in the back. 2 is the ethyl group, 3 is the methyl group. This one, counterclockwise, is S, 2-chlorobutane. You just put the R or the S out in front like you did with cis and trans. Now, what if it is drawn this way? And the hydrogen's coming to the front. You can flip it over. This can be easier to do with models, and it can be hard to do when we have larger compounds. So I want to also advise you on a trick here. So if the fourth priority is to the back, follow the rule. If the fourth priority is to the front, so wedged, coming towards you, you're just going to do the opposite. This only gets tricky when the fourth priority is in the plane, and we'll cover that in a little bit. But if the fourth priority is to the back, follow the rules. R is clockwise, S is counterclockwise. If the fourth priority is pointing towards you, then it's the opposite. So we can still prioritize 1, 2, 3, and 4. We can connect 1, 2, and 3. It looks clockwise. Right? Remember this one over here is R. It looks clockwise, which would be R, but H is coming towards you, so this one must be S. I highly recommend doing a bunch of R and S practice. You will find some extra practice from me on eCampus as well as your homework. Let's check out some other issues we can come. Oh, here's just another example of where the fourth priority is to the front. So chlorine, oxygen, carbon, 1, 2, 3. Right? It is going clockwise, so that would be R, but the fourth priority is coming towards us, so this one would be S. And that is addressed here. They're showing you how you can rotate it, or you can just know 4 to the back, follow the rule, 4 to the front, do the opposite. What to do if the fourth priority is in the plane. We'll come to that in a minute. I'm going to try and stay on track with these slides. Okay. We have talked about breaking a tie. So here's another example of breaking a tie. Sometimes you have to move further down the row, but you always move one atom at a time. So for instance, here we had a 1 on our oxygen, a 4 on our hydrogen, and then 2 carbons. And these are both CH2s attached to carbon. So when we wrote down what was attached, we have carbon, hydrogen, hydrogen, carbon, hydrogen, hydrogen. It ties again. So you'll notice we keep moving out. So we moved away from the chiral center. So now we get to this little branched piece where we have carbon, carbon, hydrogen versus another CH2 that's carbon, HH. First difference is the tiebreaker. The carbon beats hydrogen, so this side is 2, this side is 3. We can connect 1, 2, 3. What is this? It's going counterclockwise, but since the fourth priority is to the front, it would actually be R. And just some more practice in breaking ties. It is something important to recognize. It is the first thing that's different, and it's why you have to write things down in descending atomic order. So here again, 1 is our oxygen, 4 is our hydrogen. We run into a tie with carbon. Even though the carbon on the right is attached to 3 carbon atoms, the carbon on the left is attached to oxygen. Oxygen is the highest atomic number, and then the hydrogen. So oxygen will beat carbon. So it is important the way you write these down when you're doing tiebreakers. So we get 1, 2, 3, 4 is in the front. Again, looks counterclockwise, which would be S, but since 4 is in the front, this one is also R. What to do with double bonds or triple bonds. If this is our chiral center, right, we have a bunch of ties. We have a CH3, a CH2, a CH2. We have a carbon that is attached to oxygen and hydrogen. So when we are looking at these, we would go, CHH, CHH. The methyl group down here would be HHH. And then this group to the right would be OOH. You count both of the bonds out to the oxygen. If it was a triple bond, you'd count it 3 times. Well, the first difference, O wins, so this is 1. All the hydrogens lose if we're just thinking priority, so that's going to be 4. And then we have to break the tie between the 2 CH2s, and that's where I would go in and erase this. And I'd say, okay, let's move out a carbon. And then that's going to be HHH versus CHH. And there is our first tie on those 2. So the carbonyl would be 1, the CH3 would be 4, and then the longer chain would be 2, and the shorter chain would be 3. I would definitely recommend scratch paper, pencils with erasers, maybe even some highlighted pens. If we kind of want to clean this up a little bit so we can look at just the numbers. Once you get those priorities in place, right, we're going to connect 1, 2, and 3. It's going clockwise, but 4 is to the front. So clockwise would usually be R. In this case, it is S because the fourth priority is coming towards us. Now, rotating is difficult. That's why I say, like, if the fourth priority is in the front or the back, it's just helpful to memorize the rule. But the problem can happen. What if the fourth priority is in the plane? Oh, goodness, we having trouble spelling today. Priority is in the plane. There we go. You have to do something called a double replacement. So you either have to build it and rotate it, or you need to do a double replacement on paper. And so what you're going to do is you are going to exchange 4 with whatever is in the back. Now, once you do this, you are actually changing the stereochemistry to the enantiomer. So this one is first. Second, then you will exchange whatever the other 2 are. You know, you can't be guaranteed that 3 is the one in the back. So you're just changing 4 with whatever is in the back. So, for instance, if we want to, let's say, do an example like this. We'll put an alcohol here. And we'll put... Actually, let's do a methyl group in the back and the hydrogen in the plane. Now, we can set all of our atomic numbers, or we can set our priorities. The OH is 1. The CH2 connected to a carbon is 2. The methyl is 3. And the hydrogen is 4. What I would recommend is redraw this in the plane, the wedges and dashes exactly where they are in the example problem, and then just replace them with the numbers. It is harder to change groups, especially as these things get bigger. I would just put the numbers down. So now here, I am going to exchange 4 with 3 because 3 is in the back, right? So I'm actually going to make this. Oh, what did I do? Hold on. Let's take this. Copy it. Y'all are getting to watch some very exciting note-taking here. Here we go. Let's paste it where we have a little bit more room. Okay. So this is the initial here. And here we have just prepared it for a double replacement. So I'm going to just go down this way. So I am going to, again, draw all my bonds in exactly the same places. 4 is now in the back, so 3 is where 4 was. 1 and 2 we didn't touch. Now, to make sure we have the same molecule, so that's the first replacement, then you do the second. The 2 that you did not touch. So again, don't mess with where the wedge and dash are. The 3 and the 4 we've already moved. Now we're going to flip the other 2. We're going to switch 2 with 1. Now you can just use the rules. 1, 2, 3. It's going counterclockwise. 4 is to the back, so this is S. That means this here is S. You want to practice with these. I don't give you a lot with the fourth priority in the plane, but I typically give you 1 on a quiz and 1 on an exam, so you need to be able to handle it. All right, so just to review, you identify the 4 groups coming off of the chiral center. You assign priority based on atom, going down the row only if you need to break a tie. And then if you need, that's what step 3 is. If you need to break a tie, move away from the chiral center, looking for the first distance, right? And there you've got all of your all of your notes about what to do if you have a double or triple bond and how to break further ties. Then you are going to make sure that the fourth priority is in the back and use your rules. So either you're going to have the fourth priority in the back, you're going to flip the rule if it's in the front, or you're going to do a double replacement if it is in the plane. And once you have the priority set, you know how you're going to handle the fourth priority, then you're going to choose R or S based on your rule. R and S take some time to get the hang of. It is important that you take time to practice. This is going to keep ramping up. 7 is a doozy of a chapter. So make sure you spend time this week and this weekend doing practice with R and S and getting this down. In 2 or 3 weeks from now, it's going to feel very overwhelming if you don't get this skill down now. I will see you in part 4 to talk about some optical activity. Thought I would do a chapter 5, part 3.2, because there are a few practice problems on the next 3 slides. And before we move into optical activity, I think it's probably a good idea that we do a little bit of practice with larger molecules. So let's go ahead and assign R or S to this guy here. So there's 3 things shown. It is always going to be important to draw that hydrogen in to make sure you know where it is. Since the N is dashed, then the hydrogen must be wedged. And the wedge, it can go to the right or the left, but it needs to go next to the dash. Then we can go on. Nitrogen is going to be larger atomic number than carbon, or hydrogen. Hydrogen is the lowest. We have a tie between carbon and carbon. The one on the left is attached to oxygen, 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 because we go 1, 2, 3 bonds to oxygen. The carbon on the right is attached to a carbon this direction, hydrogen, hydrogen. The very first atom, we have a tiebreaker. Oxygen will beat carbon. And so I'm going to come in and just kind of erase this. The oxygen side wins. This is 2. This is 3. We can connect 1, 2, and 3, and it looks to be clockwise. But fourth priority is coming towards us. So if R is clockwise, in this case, it's going to actually be S, because the fourth priority is coming towards us. How does this affect our naming? Well, I obviously am not going to ask you to name something like this. We don't know how to name carboxylic acids, amines, aromatics just yet, and certainly not all together. So let's look at how we might name something more simple. Now, we haven't named alcohols, so I'm going to change this to our chlorines. We did this a little bit earlier, so I'm not going to go through the naming again, or the prioritizing again, but this is R and this one is S. We saw that earlier in the video, right? So we just incorporate that in the top of the name. It becomes R2-chlorobutane or RS2-chlorobutane. Now you are going to have possible compounds where you have multiple chiral centers. So again, I'm going to switch this out for a chlorine because we know how to handle that, and a methyl. If we assign the priorities, and we can do that quickly here, right? Chlorine is 1. Carbon connected to carbon, so this one right here, connected to C, C, and H will be higher priority than this carbon that is attached to H, H, and H. The hydrogen in the back will be the fourth priority. So we connect those. We got 1, 2, 3. That is clockwise with the fourth priority in the back. So this one is going to be R. Now, I'm going to write that down over here. 2R. The 2 position is R. You can see how this gets messy quickly, right? So if I'm thinking about this as an overall compound, and this is a pentane, right? 1, 2, 3, 4, 5. 1, 2. Carbon 2 is a chiral center, and it is R. So it is 2R. So then we need to figure out what... There we go. We need to figure out what carbon 3 is. So we're going to go ahead and put our little hydrogen in front, since the methyl group going to the back. is already dashed. We have a carbon attached to chlorine, carbon, and hydrogen versus a carbon on the right that is attached to carbon, hydrogen, and hydrogen versus the carbon down at the bottom that is attached to H, H, and H. So the one attached to chlorine wins, then carbon, then all H's. So it's going to be, and let me try to do this a little bit more delicately. Once I've assigned all my priorities, don't forget that the H is fourth. 1, 2, and 3 is clockwise, but the fourth priority is coming towards us. So instead of R, 3 is S. When you have multiple chiral centers, then you have to say where they are. You don't have to say where the R is up here because there's only one chiral center. So, of course, it is the R. In something with multiple chiral centers, you do have to say which is which. So, it is just the location and the designation, comma, location, designation. There could be 2, 3, 4, however many. In this one, there's only 2. So, this would be 2R, 3S, 2-chloro, because C comes before M, 3-methyl, pentane. I will start asking you to incorporate R and S in your nomenclature. That's something that I will be throwing at you all the way up until the final of Organic 2. So it's important that you get that you practice that skill. And then in part 4, we will address optical activity.